to give the money back on the screws if there's more than one defective screw in a packet. Okay, so what proportion of packages, or what's the probability that the company must replace a package? Okay, so we probably could have done this using event space and independence and all that stuff from before, but we're trying to move away from that, and the goal here is to use random variables and distributions. Okay? I'm going to set up the problem for you, but all the problems that we see after this are going to follow the same kind of flavor as this. Okay, so what's the flavor? The flavor is to write down a random variable, write down its distribution, and then apply a formula. Okay, so solution. If X is the number of defective screws in a package, then X follows, well, it follows a binomial distribution, right? Each screw has a probability of being defective, and the probability is 1%, and there are 20 per package, so that is a binomial where n is 20, and the probability p is 0.01. Okay, after that, you just use the PDF as needed, right? So the problem directs us to look at all the things that have 2 or more screws defective. We could plug in, so we have the PDF here, right? So the PDF for, and I'll come back and finish the rest of the slide in a moment, but the PDF, the chances that x is equal to k is n choose k, p to the k, 1 minus p to the n minus k. And we can just sub in a whole bunch of values of k that we like. So we could try 2, then 3, then 4, and add them all up to 20. That's a lot of work. Okay, we could also count backwards. We could also, subtract from 2 cases, the good cases where the packages are fine, right? So that'd be 0 or 1 defective screw. Okay, so we'll do that. Or sorry, package needs replacement, I guess. Okay, so it's 1 minus the probability that x is equal to 0. Probability that x is equal to 1. And that's all there is to it. We just apply the formula, and there are 2 cases here. One is x is equal to 0. It's not very likely that it's going to happen, right? It's not very likely to have even 1 screw that's defective. Anyway, written out longhand, this would be 20, choose 0, and the probability of defective screws would be 0.01 to the 0. Probability of good screws is 0.99, and that's to the 20. And then the chances of this 1 here would be the same thing, but 20 choose 1, and the powers will change slightly, so 0.01 to 1, 0.99 to 19. Interesting thing about your calculator, when the numbers are very close to 1 and then the exponents start getting really big, right? This is sort of the limiting case where, it's like you're multiplying something that's infinitesimally smaller than 1, but you're compounding all the interest, right? So you sort of get this limiting behavior, and this is where your calculator might not be at its best, right? Especially if these numbers are really infinitesimally small and very large in the exponent. Here, your calculator can manage it. This value here is 81.8%. This number here is 16.5%. Okay, so it's around 82% likely no screw will be defective in a batch of 20, exactly 16.5% of the time. Add those 2 things together, it's actually very, very close to 100%. Okay, it's only off by 1.7%. Okay, so this is 0.01686. Okay, so 1.7% of the time they'll have to replace a package. Incidentally, just as a sanity check here, okay, if you were to go the long route and add up all the things, 2, 3, 4, 5, 6, 2 is the next most likely thing, right? And if you computed 2, the probability x equals 2, it's actually pretty close to this number. It's actually about 1.5%. And 3 is even less likely. So as sort of a first order approximation, x equals 2 will get you the lion's share of this thing. Okay, so adding up the thing all the way up to x equals 20 is only going to account for a small hair of this, and that sort of makes sense. Okay, questions about this? Okay, we'll do part B of this in a moment, so keep this in mind for just a moment. I just want to go back to this slide and finish off the CDF. Okay, so we developed this PDF last time, and we've seen binomial distribution problems, but we haven't had the distribution before, right? We've used event spaces and probabilities and independence. Okay, in those problems. Here we have a really nice shortcut method, and the way that we analyze it is using combinatorics. There are n choose k ways of flipping k out of n heads, and therefore n minus k tails. Each of them are equally likely. How likely are they? Well, because it's all independent, we're going to have k p's and n minus k, 1 minus p's, and they'll scale up by n choose k. The CDF is just the summation of this thing, and it should look familiar slightly to you. Okay, so it's the sum, sorry I didn't leave myself a lot of room there, the sum from I equals 0 to the floor of x of this beast here. Okay, so we add up all the n choose I, p to the I, 1 minus p to the n minus I. Okay, I plotted the CDF of this one here, okay, so the binomial of 20.7 below, and you can see that it sort of crosses over the 0.5 mark, around 14. And this is, of course, 1, and will stay 1 after it gets to 20. Okay, this should look sort of familiar to you. What does this look like? This sort of summation, what does this look like? Doesn't look like anything? Come on, help me out. Say it again. Not a geometric series, sorry. Okay, we spent time on this in the review section of the course. No? Okay, doesn't it look like the binomial theorem? A little bit, right? Yeah, maybe, yeah. Okay, so n choose I, p, we just had x's and y's in here, but these are different x and y's, right? And so we would expect, like, if you took x to be large, right? So we sort of suspect that if we were to take all the pieces, right, sum from I equals 0 to n of n choose I, p to the I, 1 minus p to the n minus I, we would suspect that this should equal 1, right? Because you're adding up all the pieces. And you can actually prove that this is the case using the binomial theorem, because this is actually the form of the binomial theorem, right? Where this is the exponent x, that's p, and this is the exponent, sorry, the term y, 1 minus p to the n. And of course that simplifies out to be 1 to the n. Okay, so this is the binomial theorem, which has an appropriate sounding name for, considering this is the binomial distribution, yeah? Okay, so that's good as a sanity check, and that's a sort of a good cross-pollination of the math that we've seen before. All right, let's do one more example of a binomial, and then we'll go on and do balls and bins. All right. So part B of the screw manufacturing. So it's known that screws produced by a company will be defective. Okay, same preamble. B, okay, so we found out the probability of any package being defective is about 1.7%. If someone buys 3 packages, what's the probability that exactly 1 will be returned? Okay, I'm going to present 2 solutions. One is the old way, and one is the new way. Okay, and maybe you'll like the new way better. Maybe you like the old way better, but I hope you like the new way better. Okay, so solution 1. We're going to let B sub I be the event that package I, so we're going to number the packages 1, 2, 3. We're going to, B sub I is the event the package I is defective. And we know from the previous slide that the probability, let's make sure that I got that right, so the probability of B sub I is 0.01686. Okay, so in event speak, we are looking for exactly 1 package being defective. Okay, so the probability of exactly, I don't have the time to write out a whole bunch of stuff, but we would be taking the intersection of different events, right? One of the events is that package 1 is defective and the other 2 are not, right? Or package 2 is defective and the other 2 are not. Or package 3 is defective and the other 2 are not. And I'll give you a moment to catch up. Okay, and these things are disjoint events, right? So, you can use the disjoint sum rule and just write out each of these individually. So I'll do one more line here. Okay, so plus the probability that package 2 is defective and only package 2, plus the probability that package 3 is defective and only package 3. Okay, so this is, sorry, I should write that in a different color just so it stands out. Disjoint sum rule. And then we would use independence, right? And I don't want to write out more of this. This is getting pretty tedious. But this is what we would do before, right? So these are independent events. This is P, and this is 1 minus P, and that's 1 minus P. And we multiply them out. And this is 1 minus P, and that's P, and that's 1 minus P. And this is 1 minus P, and that's 1 minus P, and that's P. And we eventually get those products down. And it turns out that all 3 of these things are the same. They're just multiplied in a different order. Okay, so we end up getting 3 times P, which is 0.01686. Times 1 minus P, which is that, all squared. And then we would get the answer, around 4.9%. so that's the old way of doing things. Okay, the new way. The new way is to use distributions, and we can use a distribution here as well. Okay, so we define a random variable. We say let y be the number of packages returned. What distribution does y follow? Binomial? Okay. Yeah, it's not that binomial though. Yeah. Okay, so we've already done that for each package, but here is a different situation where we're looking at the packages themselves. Yeah, so it is a binomial, but not that binomial. Okay, I couldn't hear you, but it sounds like you called it off. All right. So what distribution is it? What does y follow? You want to try again? It's not a uniform distribution. I already told you it's a binomial. Yeah, it's not uniform. Sorry. All right. I mean, this is pretty important. I'd like to wait. I'd like you to figure it out and tell me. And I don't want you to just sit there and wait for someone else to like hoist the answer, right? I mean, this is not fun, and it's not learning. You need to be engaged with this and figure it out. I'd like it if you participated and got it wrong even better than just sitting there and doing nothing. Sorry, guys. This is it's just painful for everybody. Yeah, it's not the Poisson distribution. It's a binomial distribution. I just want the parameters. Okay, well, good. Not 4.9%, but we got binomial 3. Why binomial 3? Good. There are 3 packages, right? Each one might be returned with a probability of what? Good, with probability of 0.01686. Right? 3 packages. Each one has that probability of being defective. Y is the total number of defective packages. Okay? And we want the probability that y is equal to 1. Okay, so we'll fill in the blanks, right? So this is 3 choose 1, 0.01686 to the 1, and then 1 minus 0.01686 to the 2. Okay, that is coincidentally, and not coincidentally, it's the same as what's up here. Okay, but much quicker. Okay, yeah. On a test, we accept both ways of doing this. I mean, one is clearly more efficient than the other. I mean, generally speaking, you're going to prefer to do it this way. Like, you're not going to want to do it this way. This is actually kind of painful, like looking back at things, right? So if you do it this way, I mean, I don't know. Part of the judgment of like your answers is how good are your solutions. This is probably a better solution than this. We didn't have this technology until now, though. So this would have been the only way on your past assignment problems, right? So it depends. It's all very context specific. Okay, one more thing I just want to point out, because there's another law that you've seen before, and that's the union bound. Here we're looking at exactly one package, B1 or B2 or B3. Okay, so we could have done less than or equal to 3 times this, which is a little, it's around 5%. And it turns out to be a good bound on 4.9. Okay, so as a first order approximation and as a sanity check as well, this number is actually pretty good. Okay, good. All right, we are going to skip, well, not skip, but we'll come back to it. We're going to not do the geometric because I want to make sure that we get through Poisson uninterrupted, so we're going to do Poisson today, and we'll save geometric for Monday. Okay, so skip a few slides. We're going to go to balls and bins. And I mentioned the balls and bins paradigm a couple times, one during our review section, another on your assignments. And this is a general paradigm that fits a lot of problems. Okay, so here we go. There are n balls and m bins. N and m are going to be our 2 variables going forward. I think when we did the functions one, it was like n and k or n and r or something like that. Anyway, here's what happens. Each ball is randomly and uniformly assigned to a random bin. Okay, so let's toss them into the bins. And you can ask yourself a bunch of different questions. What's the probability of a collision? Remember collisions. Okay, so that means that 2 balls are in the same bin. We did that with the birthday thing, right? So we had balls. The balls were students, right? And the bins, each student was assigned a birthday. Well, you weren't assigned it, but more or less you were. Right? Sort of beyond your control in a way, but anyway. And we were looking for calendars that had 2, people with the same birthday, at least. or counting backwards, ones that had unique birthdays, right? Okay, so birthday paradox. Another one was when we were talking about hashing and forgery. How many different trials do you need to come up with until you end up getting a pair of, or somebody that matches your birthday, pair of the same hash values. So the balls in this case were data. The data was assigned a hash value and placed into a bin, or it had a signature. And we looked at some data management problems and forgery as well. Okay, so that's one type of question you can ask, collision. Second one, how many balls do you need before each bin has at least one ball? We haven't explored this problem yet, but we will in the next unit. And in this case, I'm going to introduce you to the coupon collector problem, where you can imagine, and McDonald's and Starbucks have had contests like this over time, where you go to their thing, they give you a colored coupon or something with writing on it, maybe a Monopoly token or whatever, and you have to collect all of them to get a free purchase or something like that. Okay, so purchase coupons, and the collection is sort of random. Essentially, you collect all the different coupon types, one of each. You can cash them all in and get something for free. This is the coupon collector problem. And you can ask yourselves, how many coupons do you need to get? How many purchases do you need to get your free thing? And how many balls end up in the most weighted bin? Okay, so what's the likelihood of an overweighted bin? This is really important for computer distributed systems, so jobs and servers to server farms, or files and disks. Let's make sure no disk is overloaded. Okay, so randomized load balancing is another problem that we'll look into eventually. Okay, but we want to have a low probability of failure. Anyway, we are going to derive something interesting about the bins today. Okay, so how many balls end up in a bin? All right. Well, here's the first question for you. Okay, first of all, we're going to let xi be a random variable that describes how many balls end up in bin number I. Okay, could be anything. Could be bin number 1. Could be bin number 5. Whatever it is. What's the distribution of that number? Good, yeah. So it's you're pretty close. Yeah, it's a binomial, right? Because each ball goes into a bin, right, and it will land in bin I with probability, I guess, 1 over the number of bins, right? So how many bins do we have? We have m bins. So it'll be probability of 1 over m for each of those things that will land in that ball. In that bin. Okay, and there are n balls. Okay, so each ball lands in bin I independently with probability equal to 1 over m, which means xi is a binomial where you distribute n things, and it lands in there with a small probability of 1 over m. Okay. Why is this not a uniform distribution? Yeah, so if you look at just one ball, its choices are uniform, for sure. But if you're, asking yourself, what's the probability that that ball ends up in bin I? It's 1 over m, right? It's like a weighted coin toss, like it's a Bernoulli, right? And each of those balls, lands in that bin with the same, 1 over m probability. So it's actually a long experiment at each of them Bernoullis. But I admit that if you're turning it around and asking what happens with one specific ball and say, where does it go? That experiment is a uniform thing. But holistically, you see it's just a different perspective. We're looking at the bin rather than the ball. Thanks for that. Good question. Okay, the probability distribution function, I'm going to write it down here. So xi equals, I don't know, r. This is, let's just take it verbatim. So this is n choose r, 1 over m to the r, and 1 minus 1 over m to the n minus r. Sorry, I crammed it in there. That is m minus r there. Time for another definition, and a lot of you have heard this definition before because you have taken a computer science course where they taught you stuff about hash tables. Okay, so it's the exact same thing that they use in hash table discussion. It's called the load factor. Okay, so the load factor is the average number of balls per bin, and we use the same symbol here that we do in computer science, data structures classes, and it's lambda. Okay, so lambda equals n divided by m, right? That's the average number of balls per bin overall, right? You've tossed all the n balls in there. Okay, so when n is approximately m, lambda is roughly a small constant. And when we sort of take the large case where n and m are both large, then we end up doing the Poisson approximation. Okay, so we're going to do a couple iterations of the Poisson approximation so you can see where it comes from. That is about as far into the derivation that I'm willing to do, is a page and a half. But you can go to your textbook and see the full thing if you wish. One of your references has the full thing. Okay, and I'm just going to do a page and a half. Okay, so first question is, what's the probability the ith bin ends up empty? Okay, so that's the probability that x of I is equal to 0. All right, so we're just going to sub in 0 for r into this equation up above. Okay, so we end up getting n choose 0, which is nice to deal with, 1 over m to the 0, and 1 minus 1 over m to the n minus 0. I love this. Especially, I get to bring out the big, fat red marker, right? Because n choose 0 is 1. Right? That's pretty easy. And anything to the 0 is also 1. So we end up with this 1 minus 1 over m to the n. Okay, so what do we do with this? Well, we're going to use this very useful approximation again that I put in a box, and we're going to use it a lot today, that 1 plus x is approximately e to the x, especially when x is close to 0. And here it is, right? M is assumed to be large. We have a large number of balls. We have a large number of bins. Okay, so we're going to use the approximation. Okay, and we can use it because 1 over m is small, so it ends up giving us something good. And the result is that the probability that xi is equal to 0, that the ith bin has nothing in it, is around e to the minus 1 over m to the n. And we just use our power rules here. We end up multiplying the powers in this case. And we end up getting e to the minus n over m. But n over m is the average load. Okay, so that's the load factor. So e to the minus alpha. Sorry, lambda, pardon me. Okay, so far so good. Okay, so that's pretty cool that it ends up giving us something that's like a e to the something. Okay, let's keep digging. Okay, so what about the ith bin has exactly one thing in it? Okay, well, we're going to do the same sort of thing. The probability that xi is equal to 1 is going to be n choose 1 this time, 1 over m to the 1 this time, and 1 minus 1 over m to the n minus 1. So let's collect some things together that are sort of nice. First of all, this is n, and we can multiply that by 1 over m. We get n over m, which is a really nice quantity. That's lambda again. And we'll do that substitution in a moment, but we'll just collect them together, n over m. That's good. And this bit here, we're going to do a similar trick. Okay, this is going to be e to the minus lambda again, but we have a minus 1 in there. There's an extra thing in the denominator. So we're just going to cleave that off. Okay, separate those two powers. Okay, and we do something similar. All right, so this bit here is lambda. This bit here is approximately e to the minus lambda again. And this bit here, it's not the greatest to have this thing around, but remember 1 minus m is pretty small. Okay, so this is going to be approximated by 1. Okay, we're just going to throw it away, okay, because 1 over m is small. Okay, so the probability of x of I, one thing in bin I, is approximately e to the minus lambda times lambda. Leave that up for a sec. Okay, so far so good? Yeah, we're going to do this one more time. Okay, we're going to do this for x of I is equal to 2, and then we're going to cut off the thing, but we're going to see a pattern, right? And this is where the Poisson distribution comes from. All right, it's really cool. All right, so let's do it. So what about probability x of I is equal to 2? Okay, so again, we're going to do the same sort of thing. We're going to sub in 2 for r this time. So n choose 2, 1 over m squared, 1 minus 1 over m to the n minus 2. Just going to focus on the choose for a moment. Okay, going to focus on the choose. That is, it's mostly all canceled factorials. The only thing that survives is n times n minus 1 over 2. And we'll leave the factorial in there. And the rest of it I'll just repeat. We'll touch it for now. And then we're going to join these things together. Okay, what we would like is more n over m's. Okay, this is pretty close to n over m squared, pretty close. And I'm going to leave the 2 factorial alone. So we're sort of write this as 2 factorial, and we're going to put an m underneath each of these things. Okay, so n underneath each of them. So that's n over m. That's good. N minus 1 over m. That's not quite so good. And this is pretty close to lambda. Now, the way that they complete the derivation to make it clear what's happening is they do something similar to this this extra piece that we're going to throw away. So let me just show what they do in the textbooks. Okay, so this is n over m times n over m, but they multiply. So to get this thing to be n over m, they have to multiply n minus 1 by n. Okay, so this bit here is exactly the same as that. Anyway, we have that to the n, that to the minus 2. Give you a moment to catch up. Okay, like, just so that it's clear, like we're multiplying top and bottom by n. That's all that happened there. Okay, but you know, it sort of makes it clear that there's lambda squared. That's what we really want left in here. This thing is going to be pretty much 1 because it's 1 minus 1 over n. Okay, 1 over n is assumed to be small. This thing is approximately 1 for the same reason. And again, we have e to the minus lambda here. Okay, so we throw away a lot of things that are close to 1. We do this e to the whatever approximation, and the stuff that we end up with is 1 over 2 factorial lambda squared e to the minus lambda, or if I'm to write it like it is up above, this is e to the minus lambda, lambda squared over 2 factorial. Okay, so it's a bunch of approximations, and we're not throwing away too many things, but again, it's an approximation. And the pattern continues. If you do n choose 3, you end up getting a 3 factorial that survives. You end up getting like lambda to the 3, and you end up getting this e to the minus lambda. This is what's known as the Poisson approximation. Okay, so the Poisson approximation. Okay, so assuming n over m equals lambda, and n and m are much bigger than r being how many balls you're looking to put in the bin, then the probability that x sub I is equal to r is pretty close to e to the minus lambda, lambda to the r divided by r factorial. Okay, it certainly fits the model that we did for 3 iterations, and you know, at this point, you know, they sort of say, well, we're just going to define this PDF, we're going to find the Poisson distribution by this PDF, and then go from there. Okay, any questions about the derivation? Yeah. Yes, n and m are very big compared to r. Yeah, 2 greater thans mean it's really big compared to r. Okay, other questions? Okay, so the Poisson distribution, there's Poisson there. Anyway, the Poisson distribution is parameterized by lambda. Okay, so the load factor for, you know, what the average size of the bin is. Okay, but it is a discrete function, even though it's got this weird e thing in there. It only takes integer values. It only has an integer number of things in a bin. So 0, 1, 2 will go, you know, arbitrarily large, but infinity is not part of the set. It is an infinite set, but infinity is not part of the set. Anyway, it's a Poisson distribution with parameter lambda if it follows exactly what the Poisson approximation was from the previous page. And if you were to develop the CDF, you would just take the summation of a whole bunch of these things. So I equals 0 to the 4 of x, e to the minus lambda, lambda to the I factorial. And of course, like this e to the minus lambda is a common factor. It's actually not a part, you know, it's not parameterized by I. So you can actually bring this thing out as a common factor. And write the sum maybe a little bit more simply. Lambda to the I over I factorial. And some of you may recognize this bit, maybe from another course, this summation. Where have you seen this before? It is a Taylor series, yeah. And it's a Taylor series for specifically e to the x, right? Or e to the lambda, as it was. Okay, so this is a Taylor series for e to the lambda. Okay, all that means, so if maybe I should get the thick marker out here. Okay, so if you were to take the whole sum, right, and the whole sum is infinite, so if you were to take the limit as x tends to infinity of this, okay, so this sum, e to the minus lambda to the I over I factorial. This bit here should equal e to the lambda. And that's good news because the CDF should sum up to 1. Okay, so that's a nice little clean bit of calculus, okay, that you can apply here to get 1. Okay, I plotted some Poisson distributions for you. When lambda equals 1 per bin, lambda equals 4. Usually lambda is a small constant. Okay, so these are small constants, and they sort of look like binomials. They sort of have this bell shape, but they're a little bit skewed towards the origin, and they tend to peter out fairly quickly. But they basically look like approximated binomials. Okay, and why do we, or in what cases do we use the Poisson? Well, whenever the numbers end up getting rather big. Okay, so whenever we have that exponentiation case where you have the numbers that are very close to 1 and you're exponentiating to something really large, normally your calculators don't handle that very well. You end up starting getting error anyway. You should switch and use the Poisson approximation. Okay, so the approximation tends to hold whenever n is large and the load factor is relatively small. N times p is small. Rule of thumb: n greater than 20 and p less than 10. Probably they should be much bigger than 20 and much less than 10, but those are sort of limiting factors. Some examples here: I mentioned the typos on a page last time. People living to 100 years of age, number of things that occurrences of roadkill in a year. There's a whole bunch of different examples you can see your textbook. Now we can do the same problem we did with the screws again, okay, using the Poisson approximation, and see what we get, because it should sort of hold, right? 20 is fairly big in the grand scheme of things, and 0.01 lambda is pretty small, right? It's going to be 20 times, so it's 0.2. Okay, so we're going to give it a try, all right? So the solution, use Poisson for lambda equals 20 times 0.01, which is 0.2. Okay, so we're looking for cases where it's more than 2, right? Or 2 or more. Okay, and we can do the same thing that we did before. We can compute the Poisson for y equals 0 and y equals 1. Okay, so that's e. Okay, so e to the minus lambda, minus 0.2, times 0.2 to the 0. That's just 1. It's not very interesting. Over 0 factorial. Minus e to the minus 0.2 times 0.2 to the 1 divided by 1 factorial. And just for context, I'll show you the values here, because I showed you on the previous go around what these ended up being for the binomial, right? So this was 0.8187. I think it was like 815 or something. This is 0.1637, which is, again, pretty close. And we end up getting this being 0.01752, okay, which is not that far off from 0.01686, right?